All right, let's take a look at the wilcoxom rank sum. Now, this idea was invented in the early 1900s, so not too long ago. This idea, we're going to be able to do it faster. It's going to be nice. You guys are going to like these tables. I know at the moment you guys are like, oh no, another table. We know the C-score table, we know the T distribution, and now we're going to learn another table. Well, it's actually pretty simple. This is going to make things easier for you. First of all, on our delta, on our alpha, I mean, sometimes you guys see that I give you a certain alpha and then I ask you it is one-tailed or two-tailed. When I'm comparing information, let me look at the two-tailed information right now. When I'm looking at comparing two samples and I want to know that one of them is different than the other. So it is to the left or to the right of the other. And I'm just looking at it is different. Like I said, I don't care whether it is shifted to the right or left. I'm looking at the two-tailed. So that's what I'm going to use two-tailed if I just want to know they are different. You know, I don't care whether it is smaller or bigger. When I want to look strictly into bigger, into if one sample is bigger than the other, or strictly less than, then I'm going to use the one-tailed. So we got to understand two-tailed, one-tailed. Again, if I want to know strictly bigger than or greater than, just one of them, I use the one-tailed. If I want to know whether it's different, I don't care if it's bigger or smaller, then I use the two-tailed. Now, what we see on our tables, we see here on the top left, let me point out on the top left, there it says N1 over N2. Well, N1 basically my sample one. And these numbers on the top represent my sample one. And then I see N2, these numbers here at the side represent my numbers from the second sample. Now here, each of these things has a TL, TU. Okay, from our acceptance region, it says the lower value that I'm going to accept, that's the TL, and the upper value, that's the TU. So the lowest and the upper values in the acceptance region. So the region that I'm going to accept. Okay, so now let's take a look. Let me do it with an example better. Let me scroll down. Use the table of normal curve areas given before. But let's see. So two probability distributions are HO, our null hypothesis. It says the two probability distributions 1 and 2 are identical. So they're pretty much look the same. That's the null hypothesis. They don't change. My alternate hypothesis says the probability distribution for population 1 is shifted to the right or left. Let me highlight this. So population 1 is shifted to the right or left. Okay, so I don't care whether it went to the right or to the left. That's just telling me, for us to know, that's basically telling me I'm looking at two-tailed. So let me write that down. Two-tailed. Okay. And let me continue reading this. Probability distribution for population 2. N1 is 5, N2 is 8, and my alpha is 0.10. Okay, so let me take a look at here. I'm looking at two-tailed, and my alpha is 0.10, so I'm looking at the bottom table. What I want you guys to do is, on the first sample, find 5. You guys see it here? Let me highlight it there. On the second sample, let me find 8. You guys see it there? Now let me find a point of intersection. Notice how I highlighted two numbers because the lower, the upper. So it says 2446. Well, guess what? That is my acceptance region. So let me back here. I'm going to say my acceptance region is going to be from 24 to 46. Okay, so what does that mean? I'm going to accept the null hypothesis if my test statistic it is in between these two values, in between 24 and 46. That is my acceptance region. But I gotta know what is my rejection region. Okay, my rejection region, I'm gonna say my T value, my T statistic has to be less than or equal to 24, or big key here, or my T statistic has to be bigger or equal to 46. So remember, my acceptance region is in between 24 and 46. My rejection region is obviously outside of that acceptance region. Now, some people might say, what if I get exactly 24? Well, it is rejected. Let me tell you why. Do you guys see how on the inequality I said less than or equal to 24? So it gets rejected. On the acceptance region, look, I'm using parentheses. So I said everything in between 24 and 46, not exactly 24 or 46, just everything in between 24 and 46. So if I do get 24 or 46, they do get rejected. That's not in my acceptance region. Okay, so for the first part, I just want you to find the acceptance region, the rejection region. Not a big deal. I want you guys to get familiarized with the tables. Now, continuing on our homework, I'm going to have you guys test some values. But then on this case, I'm not going to give you just the N1, how many are there. I'm actually going to give you some data. We're going to rank them. Okay, by ranking them, I want to say which one is the smallest. I want to rank them from smallest to largest. If we count here, see my sample one has, let's see, 1, 2, 3, 4, 5, 6, 7 values. So let me just write something here. Let me just say it, N1. N1 is 7 because there's 7 values of my first sample. And my N2, or my second sample, let me count how many numbers there are. There's 1, 2, 3, 4, 5, 6. So 7 in sample 1, 6 in sample 2. So I see that as N1 is 7 and N2 is 6. Okay. Now here it says determine the test statistic. So on the previous example, we work on acceptance region and rejection region. Now we're going to actually learn how to find the statistic. So let's see. The way we're going to rank this, I'm going to rank them from smallest to largest. Like I said, there's 13 values altogether. So 1 is going to be the smallest, 13 is going to be the biggest, and obviously everything in between. Some cases, a number repeats more than one time. So we can call that a tie. We're going to deal with those as well. So for right now, let me just start. The smallest number is 0.00. So I'm going to call it 1. Remember, I'm going 1 is the smallest number, 13 will be the biggest, and obviously everything in between. My second smallest number is 0.25. So let me call this 2. Now my third number will be 1. However, I see a tie. I see 1, 1, 1. So I don't know which one is 3, which one is 4, which one is 5. The way I'm going to do this, I'm not going to just choose one to be 3 and the other one 4 and the other one 5. Instead, I'm going to get the average of those numbers. Okay, let's remember how to do the average. I'm just going to add my numbers, 3 plus 4 plus 5. And let me divide this by how many numbers I added. In this case, 3. Now 3 plus 4 plus 5 is 12. 12 divided by 3 is 4. So what I'm going to say is all of these get a 4. So not necessarily I'm going to give one of them a 3, the other one a 4, the other one a 5. Instead, I do the average and then give them all the same thing. Okay, so I gave them all a 4. But remember, they were tied for 3, 4, 5. So my next number is 6. My sixth smallest number will be 1.10. So this is my sixth number. My seventh number, oh, I see a tie here. I see this one, and this one. Okay. Again, I'm not going to call one of them 7, the other one 8. Instead, I'm going to do the average of them. So I'm just going to go 7 plus 8. In this case, divided by 2. Because remember, I have to divide by how many numbers I added. I know 7 plus 8 is 15. 15 divided by 2 is 7.5. So I'm not going to call one of them 7, the other one 8. Instead, I'm going to call each of them 7.5. Okay, then my 9th smallest number is this one, 2.0. My 10th smallest number is 3.25. My 11th smallest number is 3.75. And then I'm going to give this number a 12 and this number a 13. Again, those numbers represent which one is the smallest. I rank them from smallest to largest. 1 is the smallest, 13 is the largest, and then everything else in between. If there was a tie, which happened twice, I do an average. Remember, I tied here on the 1. Here I had they were 3, 4, 5. I was supposed to rank them 3, 4, 5, but instead I did the average. But then there was also a tie here for 7 and 8. I just did an average and I gave each of them a 7.5. Okay, now let me add the ranks. So not the number that was initially, the ranking, the numbers that I just gave them. So for sample 1, I'm going to go 13 plus 7.5 plus 9 plus 6 plus 7.5 plus 10 plus 12. Right? Use a calculator if you need to. This happens to add up to 65. For my sample 2, let me add the rankings. So I'm going to go 1 plus 4 plus 4 plus 11 plus 4 plus 2. Use a calculator if you need to. This adds up to 26. Now, the numbers are different. The smallest number, it is going to be my test statistic. So let me say that again. When I added my rankings from sample 1, sample 2, obviously I got different numbers. The smallest number is going to be my test statistic. So in this case, 26. Right? 26 is smaller than 65. It is from my sample 2. So I'm going to call this T2 is equal to 26. Now let me identify the rejection region. Okay. Now here, I'm just checking if they are actually different, and I will tell you on your homework. You're checking whether the other population shifted to the right or to the left. So in this case, I'm going to use two-tailed, and I'm also going to give you an alpha value. Let's do here. This is going to be two-tailed. So let me write that. And let's say I gave you an alpha. Like say on the homework, I'm going to give you an alpha value. Let's just give you a value of 0.05. Okay, so looking at my alpha, I have to look at my tables. I see here, alpha 0.05, two-tailed. So I'm going to use the first table. Remember how my N1 was 7, my N2 was 6. So let me find that region here. You see these two values here? So I know my acceptance region is from 28 to 56. Let me come back here. At the side, on my notes at the side, I'm going to say 28 to 56 is the acceptance region. But then I read the question again. Identify the rejection region. So it has to be outside of my acceptance region. 28 is the smallest that I can accept. So I'm going to say for the rejection, my T2 has to be less than or equal to 28. Or I know 56 is the biggest number that I can accept. So for my rejection region, I'm going to say T2 is greater or equal to 56. Now, the test statistic that we got on our study was 26. So remember, I'm going to accept the value if it is in between 28 and 56. But we got 26. So that is in this part of our rejection section. So I'm going to reject it. I'm not going to accept it. So because my test statistic landed on my rejection region, I'm going to reject my hypothesis. If it landed in between my acceptance region, well, I will accept the null hypothesis. So in this case, I'm going to reject because it landed in the rejection region. So I'm going to reject the null hypothesis. Remember, we call that reject H of O, so, which is the null hypothesis. And I'm going to say there is sufficient evidence. Let me write that down. Sufficient evidence that the distribution for population 1 is, let me continue down here, is, now I have to remember, what was I checking? Did it move to the right or to the left, or did it move strictly to the right, or did it move strictly to the left? Well, remember I mentioned earlier, we're checking that it moved to the right or to the left. So, okay, so we're rejecting shifted to the right or left of the distribution or population 2. Right, I have sufficient evidence to be able to reject the null hypothesis, and my sufficient evidence is that my test statistic, right, in this case 26, landed in my rejection region. Because remember, I was going to reject it if it was less than or equal to 28 or greater or equal to 56. So because it is less than or equal to 28, I do reject my null hypothesis. All right, let me show you all the notes that I did. Some of you might be wondering, oh my God, am I going to write a big sentence? I will help you some of it. So some of the sentence at the very end, some of them will be there. You have to fill in what I'm missing. So like I said, you're not going to type the whole sentence. You're going to have to choose what I'm missing, okay? So there's a few words that I'm missing. So I'll help you guys on that. Again, let me zoom out so you guys can see what we did.